In 2016, an anonymous developer posted to the Bitcoin mailing list with a radical idea. What if like clients stopped asking full nodes about their addresses entirely? What if the filters flowed the other way? This single inversion became BIP158, and it quietly fixed one of Bitcoin's worst privacy leaks. First, the problem. BIP37, the old like client protocol, asked the client to build a Bloom filter of its own addresses and hand that filter to a full node. A Bloom filter is a compact probabilistic set. The node would scan blocks and return matches. The flaw is obvious in hindsight. The client just told the node exactly which addresses it cares about. Privacy gone. BIP158 flips the direction. Each full node generates one filter per block, stores it on disk, and serves it to many clients. The client downloads filters and checks them locally. The client reveals nothing. The trade-offs are real. The client now downloads a filter for every block, and on a match, fetches the entire block. That's more bandwidth than the old model. Filters only cover confirmed transactions, so unconfirmed payments don't show up here. But here's the win. The client can fetch matching blocks from different peers, mixing its queries across the network. No single peer ever learns which addresses belong to the wallet. Privacy is structural, not a promise, and the real elegance is in how those filters get compressed. Bloom filters were the obvious choice, but they're not the most efficient. BIP158 uses Golomb-Rice Coded Sets, or GCS. The trick starts with a simple observation. Take Alice's list of numbers 849, 653, 476, 900, 379. Sort them ascending: 379, 476, 653, 849, 900. Now store only the differences between consecutive values. The first delta is 379, then 97, 177, 196, 51. This is lossless. We can reconstruct the original sorted list by adding each delta to the running total. Why bother? Because deltas are statistically smaller than the values themselves, and small numbers compress better. Consider two dice. Roll them and look at the absolute difference. Out of 36 outcomes, a difference of 0 happens 6 times. A difference of 1 happens 10 times. 2 happens 8 times, 3 happens 6, 4 happens 4, and 5 happens just twice. The distribution leans hard towards small gaps. When you hash transaction data uniformly and sort it, consecutive hashes behave the same way. Tight clusters, small deltas, and Golomb-Rice coding squeezes those small numbers down to just a few bits each. So what actually goes into one of these filters? Here's where the design gets clever. For each block, the node collects two things: every output script created in that block, and every output script being spent. An output script is the locking program on a coin. It's what your wallet recognizes as mine. Notice it tracks scripts, not outpoints. An outpoint is the transaction ID plus index that identifies a specific coin. By using scripts instead, identical scripts deduplicate, and your wallet only needs to remember its own scripts to scan. Each script then gets hashed with SipHash, a fast-keyed hash function, and the output is mapped into a 64-bit number. The full script's information is truncated. Long script in, short commitment out. Truncating to 64 bits is lossy. That matters. Imagine your wallet is searching for the value 123456. After truncation, it becomes 1234. The filter happens to contain 1234, generated by some unrelated transaction. The filter says match. Your client downloads the entire block, scans it, and finds nothing belonging to you. Just 123400, 123401, coincidental collisions. You wasted some bandwidth, but you did not leak anything and you did not miss your transaction. This is the asymmetric error guarantee. False positives happen by design and are tunable. False negatives, missing a real match, are impossible because every real script you own is in the filter. There's a verification problem. A client downloading a filter cannot rebuild it from the block alone. Well, it can, but only if it already has the block, which defeats the purpose. So how does the client trust the filter? Today, the answer is comparison. The companion protocol, BIP158, defines a 32-byte commitment to each filter. The client asks several peers for that commitment. If they all agree, the client uses the filter. If one peer lies and omits a transaction, that's a false negative, and false negatives are provable fraud. The client eventually downloads the block, finds the missing match, and knows the peer cheated. False positives, in contrast, are expected and tracked statistically as background noise. 3 common misunderstandings deserve attention. First, compact block filters are not just better Bloom filters. The compression matters, but the real innovation is the direction reversal. Filters now flow from nodes to clients, not the other way around. Second, false positives do not compromise privacy or correctness. They only cost bandwidth. The true positive rate is 100%. In fact, a small false positive rate can enhance privacy by adding cover traffic. An observer cannot tell which block downloads correspond to real matches. Third, the filter tracks scripts, not outpoints. This means when a coin you own is spent, the spending block's filter contains your script too. So your wallet sees the spend without needing to track every transaction ID. Dedup, simple scanning, and one fewer data structure to maintain. There's still one loose end. Nobody is forcing those filters to be honest at the protocol level. Yet, developers have proposed committing the filter's hash inside the Coinbase transaction, the first transaction in every block, the one that pays the miner. The Coinbase has spare data fields perfect for commitments. If the filter hash lives there, miners are signing off on filter accuracy when they mine the block. Now a light client can download just 3 things: the 80-byte block header, the Coinbase transaction with its Merkle proof, and the filter itself. Verify the header's proof of work. Verify the Coinbase is in the block. Verify the filter hash matches the commitment. Done. No multi-peer comparison, no statistical assumptions, just consensus-enforced filter integrity. This is the philosophical core. The 100% true positive guarantee means a wallet can rely on these filters. Absolutely. Privacy is preserved without trust. And the larger pattern is worth naming. Bitcoin's evolution is often about inverting who holds what data. BIP37 made the client expose itself to nodes. BIP158 made nodes expose filters to anonymous clients. Each generation shifts the burden away from the user toward the network.